Okay, good morning. So, in the last lecture, we briefly talked about these concepts of testing, how you use the 5-step troubleshooting method to be able to break down a circuit and be able to find circuits where you have more than one fault. Some fundamental things to remember, particularly taking the details at each node and figuring out if you're able to propagate the error to a certain point to the output, or if you it stops at a certain point, and therefore you can act and make sure that you've covered the whole circuit, so therefore you can accurately determine whether or not there's more than one fault. So we also learned that there are a number of issues when you're synthesizing the chips. You have vias and metal ones have an invert and short. You have where you're not able to get the all the way up to the pin, so that way the signals aren't able to propagate through. And you saw some examples of that. Additionally, we kind of went over this concept here of how do you actually do a test. So you can get a chip, you hook it up to a some VHDL or Verilog code where you do some automatic test pattern generation, and you hook your chip up here to some pins, run some signals through, and you get some expected outputs, and then based on the signals you're getting back, you're able to actually determine whether or not your circuit's working properly. But timing and testing is very expensive, partially because it's very time-consuming, and also you have to make sure it's absolutely right. We talked about the FDIV Intel bug error, where it was causing a floating point error about every billion calculations, but that became a serious problem. It cost them $500 million in recall. So the thing is that in order to be able to do this properly, you have to be able to figure out how to efficiently test a chip. So the first concept, Atpg, you'll typically see it, especially if you see that in job descriptions or job interviews. What is Atpg? That's automatic test pattern generation. We define it formally as a process to determine an input sequence that distinguishes behavior between the correct circuit behavior and the faulty circuit behavior caused by defects. So the issue is, we have to be able to determine what nodes, how we can get as much coverage as possible. If you try to test every single input combination, it's very time-consuming, and that can be prohibitive. You want to use these automatic test pattern generation algorithms to reduce the number of input vectors that would be required to cover as many possible faults. So instead of doing 2 to the 32, you can cut that in half or in a third or in a quarter based on the circuit design. And so we're going to talk about these concepts of observability and controllability. And we're going to talk about this concept of fault coverage. Fault coverage is you have a certain number of nodes in the circuit, and you're trying to design these test vectors to find as many of them as possible. We'll do a couple of examples. We'll say a stuck at 0 fault at this particular node. So can we actually find that or not? That's impacted by whether or not there's fan out. That's impacted by the possibility of sequential circuits, because every single state in the finite state machine has a different combination of inputs and outputs. So you have to try to find as many of these faults as possible. By using these automatic test pattern generation algorithms, you can get fault coverage to greater than or equal to 98%. Typically, just trying to come up with your own, even in really good algorithms, will cover only about 70 to 75%. So using these algorithms that we're going to present are very helpful professionally. So we're going to finally define a stuck-at fault, where a stuck-at fault assumes all failures at nodes to stay at 1 or to stay at 0. So that example we covered last class, where we had the Xor Gate that was grounded on the B input, that assumed that stuck-at fault, B stuck at 0. So when you're doing some sort of automatic test pattern generation, what you're going to do is you're going to have some sort of, let's say you're testing an AND gate, and you have it's stuck at 0 here. So what's going to happen is, if it's 0 on the input, you're not going to be able to notice the error, because that's what it should be anyway. But if you have a 1 on the input, then you have to figure out some way to be able to propagate the error to your output. So if you have a 1 on the input for B, if you have a 0 on the input, it doesn't really matter, right? Because it's still going to propagate 0 to the output. The only way to be able to propagate the error to the output is if you have a 1 here. So what's going to happen is you put in a 1 and 1, you're expecting a 1, but since it's stuck at 0, you're going to get a 0 on the output. And that ability to be able to propagate the error to the output is known as observability, which is TGOs 6.6. It's formally defined as the ease of observing a node by watching external output pins. So if you're trying to observe a stuck at 0 fault, you have to be able to try to propagate a 1 to the output. Now, if it's stuck at 1, that means we put a 0 here, and then if we put in a 1, we're expecting 1, 1 to get, should get a 1, but we get we should get a 0, but we get a 1. If we put in a 0, then it's still going to be 0 on that output. So we have to have this idea of observability, and the second part here is controllability. The ease of forcing a node to 0, 1 by driving the input pins. So for an AND gate, in order to drive a 1 to the output, you have to have both 1 and 1 on the inputs, correct? Now, if you want to drive a 0 to the output of an AND gate, you only need to have 1 0 or the other 0. Now, this becomes helpful in Atpg because if you know that you only need one of them, then you don't need to put inputs on the other pins. So if you have a 6-input NAND gate and you're trying to propagate a 0 to the output, you don't even have to worry about the 5 other inputs. So trying to use these principles to reduce not only the number of vectors, but the number of inputs required in the vector becomes important. So understanding controllability makes, particularly we're going to be covering 2 algorithms, how you do it without fan out and how you do it with fan out. And these 2 concepts become very important to be able to try to reduce the size of your test vector. And so the other part are repeatability. So especially in sequential circuits, you have to make the same error happen again and again. Right? So if you are dealing with a D flip-flop, you have to worry about how the error occurs when your clock is 0 as opposed to your clock is 1. How is it affected when you're in your hold and setup time? How is it affected when you're trying to propagate a token to the output? How is it affected when you actually have your switching occurring? So if it repeats but then stops repeating, there's some sort of input combination or some sort of hold or delay time that could possibly be affecting your error. So if it's intermittent, it's maybe because you haven't properly accounted for noise margins. So sequential circuits are very important in being able to hold a value through feedback. So if you haven't accounted for your noise margin properly, you might have loops and then it starts at 1 and then eventually kind of trails off to 0. So that's kind of an intermittent fault. So, but if you put it in again, you should be able to get that same error using the same set of conditions. So your test vector has to account for this. And then I kind of alluded to fault coverage earlier. The percentage of the chip's internal nodes checked by a set of input vectors. I'm going to scroll up to put 6.8 at the top. So when you try to propagate errors through a circuit, we're going to worry about this concept called composite logic. So the general idea is when you have a normal, let's say you have a normal AND gate, right? And you have 1 and 1 on your inputs, and you know you're going to get 1 on the output. But let's say you have a stuck at 0 fault. So it's stuck at 0. That means we're going to get 0 on the output, right? So the idea of composite logic is comparing what should be true versus what is true in the circuit. So what we're going to have is you're going to have 1 on your input. That's perfect. Now, the notation is it should be 1, but it is 0 on the input, meaning it's stuck at 0. You have your AND gate. And then what should happen is you should have should be 1, but is 0 on your output. Now, composite logic are values used to keep track of error propagation by considering both the fault-free circuit N and the faulty circuit N sub F. Now, the notation that's used, so and we're going to be using this in the subsequent TGOs and subsequent circuits, is when you have 1, when the circuit should be 1 and it is 0, that's denoted by the value D. But if it should be 0 and it is 1, it's denoted by D bar. And then if it should be 0 and is 0, it's just 0. And if it should be 1 and is 1, it's just 1. And so let's say we have a NAND gate. And we have an instance where we have a stuck at 0 fault. So we have 1 on the input, and it should be 0 and is 1. So we're going to denote that as D bar, right? So by doing our truth table, we know that it should be 0 and is 1. So if it's 1, 0, it should be a 1 on the output, right? But it's going to be 0. So 1 in D bar on the input of a NAND gate is going to give us D on the output. Does that make sense? And in the next topical guide objective, once we scroll past it, we're actually going to show the truth table for an AND gate, an OR gate, and an XOR gate. And knowing that will be very helpful for you to be able to propagate these errors through when doing these algorithms. Does everybody have fault coverage? Yeah, okay. So here's the truth table. We've defined value and value faults. 0, 0, 0, 0, 0, 1, 1 is 1, 1, 0 is D, 0, 1 is D bar. So you have, here's where everything kind of works fine. So you have an AND gate, 0 and 1. So 0 and 0 is going to be 0. We know that 0 and 1 is 0, 1, 0, 0, and 1, 1 is going to be 1. So then the rest of the truth table is what it should be versus what it actually is. So we have D, D bar, and undefined, right? So I'm going to scroll up a little bit here so you can see. So when you have a D on the input of an AND gate, that means it should be 1 and is 0. So D and 0 is going to give us 0 every time because it doesn't matter if it should be 1 or should be 0. It should be 1, 1, 0 is still going to give us 0. It actually is 0, it's going to give us 0. So the controllability of this test doesn't work, right? Because no matter what, it's still going to give you 0. It's still going to give you the correct value. So 1 in D is just going to give you D, because if it should be 1 and 1, it's going to give you D on, give you 1 on the output. If it should be 1 and is 0, it's still going to give you 0 on the output. So it matches with D. So 1 in D bar becomes the same thing. So what happens if you have multiple faults? You have D and D on the input, right? You have D and D on the input, then you should have 1 and 0 on both of them, right? So what the circuit should be, it should be 1 on the output because it's 1, 1, right? But what's actually going to happen is it's going to be 0. So it's going to be 0 there. So it's going to be D again. So that's why that is the case. And from there, D bar and 1 is D bar. D bar and D bar is the exact same thing. It's going to give you D bar on the output for an AND gate. So knowing this, you can actually just kind of figure out what a NAND gate should be. OR gate, same thing, 0, 1, 1, 1. 0 in D is going to give you D. 0 in D bar is going to give you D bar. Same thing, 0 in D, 0 in D bar. Now, if you have a 1 on either input for an OR gate, you're going to get a 1 on the output no matter what. So if you have a 1 on the input and you have D bar, it's still going to be 1. If you have a 1 on one of the inputs and it's unknown, you're still going to get a 1 on the output. So the controllability of the OR gate is dictated by a logic value of 0. If you put a 0 on, if you put a 1 on either input, 1 will be propagated to the output. The observability is not very observable because you can't propagate the error to the output. Does that make sense? So D and 0 is going to be the actual values propagated out. Now D and D, again, you put D on the input. If you put D and D bar, here's what should actually happen. You're getting 1, 0 and 0, 1 on the, this should be an OR gate, sorry. if you have 1 and 0 and 0 and 1, so it should be 1 and 0, right? That means you're going to get a 1 on the output. What actually happens is you have 0 and 1 on the output due to the errors, so they're both going to be 1. So in this case, this is why D and D bar is 1. So in a weird sort of way, you have 2 errors, but you have propagated the correct value on the output. So this is why testing can be tricky, and that's why coming up with your own set of vectors without doing Atpg covers only 70 to 75%. Because often you'll still get correct values on your output even though you have 2 errors on the input. So using these algorithms to try to narrow down your fault is very useful and will save you tons and tons of time. And as I mentioned last class, this is a very important skill which many companies need. So if you become good at it, you'll become handsomely compensated. And so last but certainly not least, and I think you guys probably all jotted this down by now, Xor Gate, it's one of the inputs is 1 and the other is 0, then you're going to get a 1. But if they're both the same, then you'll get 0 on the output. So then being able to derive this using D and D bar, if D and D are both on the inputs, well, that means no matter what, they're going to be the same. So if they both should be 1, but they both are 0, then you're going to get 0 on your output, right? So if they're the opposite, that means that it should be 1 on one input and should be 0 on the other input, but the faults are going to cause it to be a 0 on one input and a 1 on the other input, and therefore you're going to get 1 here. So having multiple errors on the inputs will actually generate correct values. So I alluded to the controlling values for AND and NAND gates are going to be 0, meaning if you put a 0 on any one input, you'll have a value propagated. For AND gate, it's going to propagate a 0 to the output, and NAND gate is going to propagate a 1. I'm sorry, the TGO ends here. For OR, if you put a 1 on either input, you're going to propagate the value to the output. For OR gate, you're going to get a 1, and for a NOR gate, you're going to get a 0. So does that make sense? Does anybody have any questions before we move on? Okay, so what we're going to do is we're going to revisit this full adder circuit where we had our stuff at 0 in the XOR gate. So here we have multiple errors in the circuit. So what I want you to do for this specific problem is I want you to find the composite logic values for the input combination 1, 1, 1. So the composite logic values, we're actually going to figure out what should be happening in the circuit versus what it actually is happening in the circuit. So, I'm sorry, for 1, 1, 0. So we have 1, 1, and 0. So we define everything's fine here because we have our 3 inputs, right? So what's going to happen, we get to our XOR gate. It should be a 1. We should get 1, 1, so it should get 0 on the output, right? But because it's 1 and 0, meaning the XOR, the second is grounded, we have that stuck at 0 fault, we're actually going to get 0, 1. So what is that notation?
D bar.
It's going to be D bar, right? So we have 1, 1, 0, and D bar. So for this one, we have a 0 coming in here into the second XOR gate, right? So you have D bar and 0. What's the output going to be? It's going to be 0, 1, 1, so it's going to be D bar again, right? So here we also know that the circuit is, in the previous problem we proved that this circuit's working fine, except the fact we have D bar here, right? And 0. So if we have a 0 on the input for an AND gate and D bar on the input, what's the output going to be? I'm going to hide it so you can't see the solution. If I have D bar, because we have the D bar is the output of this XOR gate, right? So we have D bar in one of the inputs, and we have 0 as our other input. So think back to controllability. For an AND gate, what's the controlling value? 0. So that means if you have a perfectly working circuit here for 0, what's this output going to be? It's going to be 0 no matter what. So the composite value is going to be 0/0 or just 0. And then again, you have 1 and 1 working for the AND gates. So it's working fine. You have a 1 and a 0 here, and then you're going to get a 1 on the output. So the actual solution is just, this is what you guys just derived as a class. It's the same thing, except this is the composite value notation. So does what we did to figure that out and the notation that we're using, does that make sense to everybody? All right. So as you can see, because going back, we figured out by splitting in half that if you ground both of these inputs, and you fix only one of them, it's going to create a different set of outputs, right? The reason why is because based on these inputs, we have an error propagating here. It's going to propagate to the output. But it's only going to be in certain circumstances because 0 is controlling this AND gate. The only time the error is going to propagate, if we look back to that truth table, is when carry in is 1, because it can propagate V bar to the output. So that's where these concepts of observability, controllability, and coverage come into play. So we're going to present 2 algorithms today. So when I talk about the problem, when you see it in industry, you're going to see something called an LSAV fault. So L means we have our node. So if, for example, we have an input, this would be A stuck at 0 fault, right? And the notation is important because L is going to be what you're inputting into your algorithm. So L is the node, and V is the value that we're putting in. So in your function, you're going to say, I need to justify this particular node at this value. So I've called this main test generate. So we have an initial stuck at value node and an initial value that we want. So from the previous problem, we have node N1 stuck at 0. And it's going to basically set all input values to X, because right now, if they're unknown or undefined, then it's possible that you may not need to include it in the test vector. Now, this justify function, you're going to put in V bar. And here's why. If we went back, remember here, we have our stuck at 0 fault, right? So we need to determine this V bar means that we want 1 to go through, and that's going to have some sort of propagational effect on the circuit, right? So we're going to justify the inputs by saying we take the opposite of the stuck at fault, and we need to figure out how to propagate that through the circuit. Well, if we have a 1, then we need to have a 1 here, right? So this function, this portion of the algorithm is formally defining that intuitive process that we just did. So in order to do that, you had to figure out, first, if L is a primary input, that means return. That means if we're here and we figured out L, that means we've gotten to the primary inputs and we can terminate the algorithm. In our next example, I'm actually going to show you going step by step how this actually works. But if we continue, this means that L is a gate, right? As the output of a particular gate. That means we're going to find the value C as the controlling value of L. This is why knowing the controlling values is important. And then we're going to define I as the inversion of L. And so that invalid is going to be V XOR C. So let's say we have our stuck at 1, right? So we're going to call justify, we're going to call node, we'll just call this N0. We would call N0 and 0, right? We get into justify, we set the node L to value V. Since it's not an input, we just do C as the controlling value of L. So it's that would be some previous gate. If it was an OR gate, we'd set it to 0. And if it was if it was an OR gate, we set it to 1. If it's a NAND gate, we set it to 0. We invert. And the reason we do this is we're trying to figure out how many inputs we need to do, right? So for each input j, if this is equal to C bar, then each input j of L, we're going to continue to justify, because we need to be able to justify in order to determine all of the inputs to our circuit. So then once we've justified, right, if V is equal to 0, then we're going to propagate D through. We're going to propagate that node and D. So first we have to justify our inputs before us, and then the next step is to prove that it actually continues to propagate to the output. Because the whole objective of the algorithm is to see if a specific set of test vectors propagate the error to the output so we can actually observe the error on the output. So that's why we have our main algorithm, and our two subs are justify, determining the test vector, and then propagate, seeing if that particular portion of the test vector propagates the error to the output. So we define the function propagate as the node, and we have the value, we call it error, so it's either going to be D or D bar. And so we set the node to that error value. If L is a primary output, that means we've reached the output. Then we're done. That means we've succeeded. Otherwise, we're going to set K as the output line of the gate driven by L. So we have in our AND gate, and we have our stuck at value on the input. Well, the output line of that gate is going to be K. So this means we have our stuck at value. This is L, and K is going to be this line. So this will be K. C is the controlling value of K. So if it's an AND gate, it's going to be 1. If it's an OR gate, it's going to be 0. And then K is going to be the inversion of that value. And then for each input J of K other than L, we're going to call this justify value again. Because if we haven't propagated, that means to primary output, that means we have another gate, right? So once we move on to the next gate, we have to justify that all the other inputs that we've determined still work. And then once we've done that, then we can propagate the error XOR I. So example 6.4, I'm going to show step by step. I know this is a lot I'm just throwing at you at the moment, but step by step we're going to walk through this, and then I can show you what the process that most of you will do when you actually present this on an exam. So here we have a circuit. This is going to be examples. So we have generated a test for the F stuck at 0 fault. So again, we had our LSAV. So our initial value that we're going to be putting into main test generate is going to be this node F. Right? So the first one when we call that function, justify is going to be the inversion, right? So that first justify, before we even look at it, it's going to be justify node F and 1. Right? So justifying it, we're doing it backwards. Propagate, we're doing it this way. And then what's going to happen is once we get here, then we have to justify it backwards this way. And then once we get here, we have to justify it backwards this way. So our goal is to get some sort of input test vector that we need to put here in order that guarantees that we can actually propagate D or D bar to the output. So that's the objective of this algorithm. Now I should note here that this circuit does not have any fan out. And so we're going to present a second algorithm called the D algorithm that I'm going to show you an instance where this algorithm would fail when you don't have fan out, or when you do have fan out. Why you would want to choose? Well, here let me ask you this question. If it's going to fail in certain circumstances, why present it in the class?
So you know how to do it.
Well, not just so you know how to do it, but why specifically should you know how to do it? Adam?
Because it works in certain circumstances.
Because it works in certain circumstances, but the other one's going to work in all the circumstances. So why would I present this one? I promise I'm not wasting your time.
It looks pretty clever.
It's pretty clever, and if it's clever, what does that mean about running it in a computing environment? Fast. So if you know your circuit doesn't have fan out, run this one because it'll be a lot faster than having to do the D algorithm, which which is a little more time intensive, especially if you're trying to generate a set of test vectors to find as many nodes as possible. Okay, so I've copied the circuit here. So this is our initial circuit. And so the first thing we're going to do, since we have F, we call F1 because we call the inversion of the value. We're going to set I equals to 0, C equals to 0, and invalid is going to be C XOR L, which is going to be 1. Now, here's why that 1 is important. The 1 is important. That means you have to do all of the inputs, right? So here, what we're doing is we have to do both A inputs. So both inputs to this AND gate. Because since we're trying to get a 1, and intuitively what this means is we have a stuck at 0 fault, so we want to get a 1 here, right? Because that's what's going to trigger the fault. So in order to get a 1 there, we have to have both inputs be 1. So what's doing is we're calling, what the function is doing is calling both A and B, and in the function it says if it's a primary input, stop, which means it's just going to return the value. So we designate A and B as 1. Intuitively, what we're saying is it's stuck at 0. It needs to be a 1 in order to trigger the error. What do I need to get a 1 here on the gate? So if this is an OR gate, what would we want to do? Just call one of them. Exactly right. You get a 1x or x1. So that's why in the algorithm before it said if inval is equal to 0, select one of the inputs. But if it's equal to 1, you have to do all of them. And we have an example a little later. We actually have an OR gate here where we're going to do that. Okay, so there's there's multiple ways of expressing it. The one that you're probably going to, I should note, you can use this as reference on your exam since you can use the video. But for those of you who are writing the answers, this is the answer I'm going to want you to write here. So we're going to go over how that intuitively makes sense. But for the time being, use this as a way we're making the algorithm make sense compared with the circuit. So we've propagated, we've justified our circuit. So 1, 1 is going to be in the input. So it should be 1, but it is 0. So that's going to be D. So what's going to happen is we are then going to propagate F and D to this output, right? So that's where this function call comes in. So here, what the algorithm calls for, K is equal to H. That means that's the node that we're controlling, right, on the output. C is going to be equal to 1, and because the controlling value of OR gate is 1. If you put a 1 on either input, then you're going to get a 1 on the output. Does that make sense? If it was an AND gate, you would call 0. Because if you put a 0 on either gate, you get a 1 on the output. And then I is going to be equal to the inversion of H. So what this means is we have to see how we propagate this. So if we have we have D here, and we want to propagate this to the output, right? That means we would say that this is going to be equal to 0 because we want to ensure that this propagates, right? So then what we're going to do is we're calling justify here. So now, since we do this and we determine, we do the same process with the AND gate, but the end result's going to be inval is equal to 0. What this means is we only need one of these two inputs to be set, right? So here in the solution, I've had 0x, but both of these are correct answers. Excuse me. Both of these are correct answers. You can do 1, 1, 0, x, or you can do 1, 1, x, 0. Because you only need to trigger one of those two inputs. So what we have right now, we have 1, 1. We'll do 0 and x. We put 0 here. We have D here, right? So that means we have D on this output, right? So again, we have an AND gate. So what does this need to be here to propagate the error to the output? Correct. So what does that mean E needs to be?
0.
There you go. So this becomes D on the output. So we've propagated the error to the output using this test vector. So what you would do if you were trying to generate a whole set of test vectors is you would, actually I'm getting a little ahead of myself here, but let's say this is the solution here that we just did. We started here, 0, so we set it to 1, we call justify. In order to get a 1, we have to have 1, 1 on the input, right? So then this becomes 1, 0, so it becomes D. In order to propagate, the propagate function determines what we need to do. So this becomes, we need a 0 here to propagate D to the output, right? So in order for 0 here, we're going to justify. We only need one of them, so we have 0x here. So in order to propagate this error, D, to the output, we need this to be 1. That means we need this to be 0. So our input function becomes, our input test vector becomes 110x0 or 11x00. Yes, Thomas.
For the A and B input and gate, whenever we put 1, 1, why are we getting 1, 0?
Okay. Because of the composite logic function. So the problem is stated as this is a stuck at 0 fault, right?
Okay.
Correct. So what I mean, this is a good question, so I just want to make sure I emphasize this enough. So what I mean by 1, 0 is when it's 1, 1, the function should be 1, but it actually becomes 0. Yes?
So if we want to propagate an error through a type of gate, we need to use like the opposite of the controlling value?
Mm-hmm.
Okay.
Correct. And that's where the observability becomes. So the controlling value is, if this is a 1 here, we have a 1 on the output. And that's why knowing those truth tables is so important, because you don't want to get an instance where your test vector, let's say you put 1, 1 here, this puts 1 here on the input, you're going to get the correct value on H, and so you're not detecting the fault. Any other questions? So, but what I just did is typically what most of you will do if you're trying to figure out on an exam. And this is a perfectly acceptable answer. And what you want to do, if you feel like there's any confusion, start making notes, refer to this. This is where I will start grading, but then if you put notes on the side, that's where a lot of benefit of the doubt will come into play. So I go, oh, I see where you made your mistake, and from there I can do error carried forward. So now here's the example of what I was talking about. So let's say we have this node here is stuck at 1. That means we want 0 on this input, right? That means we justify, we get 1, 1, and 1, right? So what's going to happen is we get a 1 here. Whatever D is going to be, this is going to be 0 because it's a Xor Gate, right? 1 here, 1, it's going to invert to 0, so it's a Xor Gate. So what's ever going to happen, we're going to get E here, right? So that means no matter what, we're always going to have 0 on this output. So it's stuck at 1. Well, 1's going to propagate E. So what happens is, no matter what, we're either going to get 0 or whatever the value of E is on the output. We have failed to propagate the error through the circuit. And the reason why is because we have fan in, and so we have fan out on these nodes, which reconverge with the error. Which means the test vector that we've come up with to try to get this value reconverges and has an impact on the flow of the values. The result is it's not detected using that. So you actually have to use a different algorithm. When you get what's known as a contradiction, then we actually kind of backtrack. We use a backtracking step. And from there, we actually figure out what the correct value should be. And so I've already kind of discussed this, why we would want to use it. The previous algorithm, it's simpler for instances when you don't have fan out. It's going to save a lot of time, as you guys will see. But by using the D algorithm for circuits that you know to have fan out, you'll improve your fault coverage. So I also kind of included a potential graduate level problem. This is what I was going to discuss before. So what you'd want to do if you had this kind of circuit and you want to generate the minimum set of test vectors, what you would do is you would select each node. You go A3, A2, 1, A0, N1, N2, N3, and Y, and you would say, you would do the previously presented algorithm for stuck at 0 and stuck at 1. And these are examples of A3 stuck at 0, A2, A1 stuck at 1. And what you would do is you would determine, if this is 1, 1, 1, 0, and this result is it can be 0, 0, 0, 0, 1, 0, or 1, 0, 0 because of our XX values. And what you would do is you would then say, you would do them all, and then the minimum set is that minimum number of test vectors. So instead of requiring 16, I believe the answer is actually 7 for this particular example. So instead of having to go 16 combinations of inputs, you only need 7 combinations to find every possible stuck at fault. And the algorithm that I just described is that. So here we're going to be starting to talk about some concepts that you need to know for this D algorithm. This backtracking strategy, which I kind of alluded to earlier, the general idea is we see the value that we're propagating, and then we compare if this propagated, this means on the outputs we should get this. However, because of the fan out, and we backtrack and we see what's going to be propagated, there's eventually going to be a contradiction. One way of going through the circuit is going to give us a 1. The other way of circuit is going to give us a 0 or a D or D bar. And if we have that, we need to actually systematically go back to where the contradiction took place, start there, and move the propagation forward. So this algorithm presented is kind of the fundamental testing algorithm for these kind of fan-out circuits. It was developed by IBM in 1966. And the general idea is you kind of you separate all the nodes and gates into these concepts of D frontier and J frontier, where you're trying to figure out which ones have values on the input that can't propagate to an output, or which ones have a known output but are not completely implicated by all of their inputs. So we're going to define D frontier formally as all gates whose output values is currently X, meaning we have an undefined value, but have one or more error signals on their input. So we have an OR gate, right? And so we have propagated, let's say we've propagated D bar to the input, right? But we don't know the output. The reason why is because we haven't propagated the other input yet. So if it's 1, well, guess what? It's going to be 1 no matter what. But if it's 0, then you're going to have D bar on the output. Now the J frontier is all gates whose output value is known but are not implied by its input values. So we're going to have some sort of output combination, but it's not necessarily implied by the input values. We have unknown values or error values or a contradiction. And so the objective of the algorithm is to get everything out of the J frontier. And we're going to get down to this last thing where we have what's known as a unique D drive. Let me scroll up here for those of you in the back. A unique D drive is when only one gate remains in the D frontier. That means we only have one gate left. Every other gate in the circuit, our output values are either known, or there are no inputs in the circuit. No inputs that have error values. So we're trying to get all of these circuits out of the J frontier and eventually get down to this one last unique D drive. And from there, you know you have yourself a solved test vector. Now, when you're doing this, we have our input values that we calculated based on our truth table, and we have a result of that gate. Now, when that gate has a result on it, there's going to be some sort of process where that propagates to the rest of the circuit and reaches an output. That propagation is what's known as an implication. We have implied that if this is 1 and 0 on the inputs of this gate, or it's 1 in D or 1 in D bar, the consequence throughout the rest of the circuit is this. So the 3 steps are for this implication process. We calculate all values that can be uniquely determined by the implication. We check for consistency. This is a very important part. And when we do the example, you'll see what I mean by this. So consistency means that 1 is going to be on the output based on this implication, but the implication propagates through fan out, and it's supposed to be 0 or D bar. That's a contradiction. And therefore, we have to backtrack. And assign values in 3, we're going to maintain the D frontier and the J frontier. And in the example we're going to be going over, I'll actually, in more detail than I'll expect from you on an exam, describe what's going into the J frontier, what's in the D frontier, etc. And so the D algorithm, we're going to be we're going to kind of using these justify and propagate values. So we have our circuit, we have our set of nodes, we have our stuck at node, and we have our stuck at value. So initially we're going to set all the other nodes to X, and we're going to put all the gates in the J frontier. So we don't know if the gates are implied by the logic values. So we're going to set node to the value. So while the primary outputs are X, we've already set the nodes to X, we're going to determine the implication of setting this node value to V, and we're going to check the results. If the circuit fails, determine the gate that caused the failure and set the input node gate as that value. So the reason why we're going to set that specific node to the value is because that contradiction is caused by some sort of value that has to be. That contradiction exposes what we have to do, and then from there we can propagate and justify and determine our correct values. So we don't want the D frontier to become null. If the D frontier becomes null, that means we failed. That means we're unable to determine a stuck at fault. So there's approximately 98% where we get fault coverage, but there's still going to be 2% where there's an issue. So if you're doing an Atpg algorithm and you determine that there are certain nodes that can't be detected by a test vector, then you actually have to physically test every single chip of those specific nodes. However, by determining the set of input vectors, you can just run those, and if they all work, that means you know 98% of the work is done. And then you just have to physically check 2%, instead of having to check 100%. If you remember from 385, I talked about this concept of the tyranny of numbers, and that Jack Kilby invented the first integrated circuit on silicon. Before that, everybody thought you had to connect every single piece in the computer, which is why computers are so huge. So imagine trying to do this without having input test vectors and having to go through and try to test every single portion of your giant computer where everything's connected to everything else. Now you don't have to worry about that. Now your timing for your testing is significantly reduced. Now you cut that down from everything's connected and you have to test 100% of them to things flow through a circuit. You only have sequential elements or gate elements, and you only have to test 2% of them physically. So we're about to go over an example of the D algorithm. Excuse me. We're about to go over an example of the D algorithm. So in case anything makes sense or doesn't make sense, hold on to your question, and then after we go over the example, I'll explain. So we have this circuit here, for example, 6.5. Use the D algorithm to determine the input test vector required to find the indicated fault. So here, we have indicated we have this node, this input to G0, which is the NAND gate, is stuck at 1. So where this becomes problematic is, let's say A is 0. It's going to trigger it there. But here's the thing. The actual value is going to go as the input to the NAND gate. So that input to that NAND gate is 0. That means we're going to have 1 as the output of H automatically, right? And so you can see that it has some sort of impact on the output. So here's our first actual step. We set A is equal to 0. So therefore, like I just described, we know H must be 1 because it propagates here. And then 1's going to be on the output. And that's good because ultimately we want to be able to propagate this output to this node N here. And 1 on the input of a NAND gate doesn't necessarily mean that we can't propagate it yet. Because if you have a 0, we'll propagate a 0. If you have a 0, it'll propagate a 1. If you have a 1, it'll propagate a 0. If you have D, it'll propagate D bar. If you have D bar, it'll propagate D. So this is desirable. If we get a 0 on this output, that means we have created a contradiction or an error in being able to propagate it, then we have to go backwards. And so we have defined our D frontier as G2, G4, and G6. Now, here's the other thing. I skipped a step, sorry. So we have 0 here, right? So this becomes stuck at 1. We want to propagate the error to the output, right? So in order to propagate, you trigger 0, it becomes 1. In order to propagate that error to the output, you have 1, 1 on the inputs for B and C, right? And the reason why is because if it's 1, 1, 0, you'll get a 1 on the output. If it's 1, 1, 1, you get a 0 on the output. So that means B and C have, A has to be 0, B has to be 1, and C has to be 1. So that means you should get 1, 1, 1, 0 on the output, but so it should be 0, but you get a 1. So you're actually going to have is you're going to have D bar. So this becomes attached to 2. D bar becomes 4, and then it's fanned out to 6. So now that we have an error on those inputs, that means that G2, G4, and G6 are in the D frontier. And we don't have all of the inputs for G1, G3, G5, and G7, so that becomes our J frontier. So step 2, now that we have H is equal to 1 and A equals 0, now we're going to try to select D here. So if we have 0 here and we have 1 here, right? So it's a NAND gate, so no matter what, it'll propagate through. But let's say we select D is equal to 1 as our input. This is going to be our guess. So now we've taken our guess, and we're going to do the implication. The implication means that D bar is equal to 0, but here it's also propagated 1 to this input, and we have D bar there, right? So now we take G1 out of the J frontier, because now we know both inputs and there's no error. So now we've put D bar here and 1. So that means because it's a NAND gate, we're propagating D bar, which is what we want, right? So that's why we kind of selected 1 for this one. Because if it's a NAND gate and you have a 1, that means you're going to propagate the value of the error. But if you have a 0, you're going to propagate the opposite of the error. So that's why we selected that. So that means we still have, so now we have 1 and D bar, and we know that D bar is here. So that means that G2 is out of our D frontier, but now that we've propagated an error to the input here, that becomes, now our D frontier contains G7. And since we took these errors, we got these out, we've now reduced our J frontier to G3 and G5. So now we're at step 3. So D bar is 1, right? And we have G here. Now we have to try to select E. So what we have to do is we have to select the best way to propagate the NAND gate to make all values equal to 1. So ideally, we have 1 here, D bar, and ideally what we could do is just go 1, 1, 1, and 1, right? So therefore, we want 1 to be on the output, right? And we have B is 1 here, so this comes through here to the input of G3. So we have 1 here. So if we want an input of the, if we want the output of this NAND gate to be 1, that means we need E bar to be 0. So E bar must be 0. That means E must be 1. But let's see what happens. If E is 1, if E is 1, then that means it's propagated to this input of G4, right? And since we have D bar here in 1, then K must be equal to D bar. However, previously we said 1, D bar, 1, 1, 1, 1, right? Because we've propagated D bar to a value we've defined as 1, that means we have our contradiction. So therefore, we have some sort of mistake. So therefore, we can't define that value as E that way. So therefore, we have not moved anything in or out of our J frontier or D frontier. So the next step, since E1 made the E equals 1 made the contradiction, then we're going to start with that value. As I mentioned earlier, if that made the contradiction, that means we're going to try to find the implications. Instead of saying that all of these must be 1, we still remain H is equal to 1 and I is equal to D bar. But again, we get rid of all of those 1, 1, 1, 1, 1, and then we just say, well, let's make E equal to 1 and see what happens. If we make E equal to 1, that means E bar is going to be 0. That means our error is going to propagate through, right? Now, where the contradiction is eliminated is D bar is going to propagate through. We have a 1 here, which means D bar is going to be there. So since we've no longer defined it, what we're going to say instead is that we want this node to be D bar. Now, I'm going to scroll here just a minute. So now we have 1 and D bar, and then we have 1 here because we have 1 and 0, right? And now we have 1 here and D bar coming out of the NAND gate. So now we have D bar. And this works because we've propagated the same error twice to the input of this NAND gate, but it's still going to work. If D becomes 1, if we have 1 and 1 here, and D bar, if we propagate a 1 to this output, then we're going to still propagate a 0 on the NAND gate. If it's 0, then a 1 will propagate, right? And since we haven't guessed these, there's no contradiction. Does that make sense what I've done? That's where the contradiction comes in. So from here, now that we've gotten G3 is going to have a 0 here, a 1 there and a 0 there. That means it's out of our J frontier. So now we've narrowed down J frontier to G5. So we're getting close. So we have G5 as our J frontier, and that makes sense because we haven't defined F yet. And G7 and G6 we still have errors because we have an error here, but we haven't defined it. And we haven't quite propagated this error all the way through. So not all of the inputs are defined, so therefore that's still in the D frontier. So the next step is we want to take this guess again. Recall earlier we set all 4 equal to 1 because we want to propagate it through on the NAND gate. So what we're going to do is we're actually going to say, well, let's see what happens if we just make these last two the last two 1, right? That would make life simple. Well, is that going to work? Well, we have 1 on the input for G5, right? So we don't have a 1 here for an AND gate. That means F bar has to be 0, which means F has to be 1. So now we're going to check our implication. We have a 1 here. We have a D bar here, right? So it's going to be on the output of G6.
D bar.
And if I put D bar here, what does it mean? this is where our contradiction is coming, right? So therefore, we get rid of that. So it's going to be what we define here as step 6. We just say f is going to be equal to 1, right? And then we're going to get 1 still on the output, but this will allow d bar to propagate here, which means G5 is going to have our J frontier. Our J frontier is empty. At the same time, because we have the error and we fully have values determined, means G6 is going to be taken out of our D frontier, which means G7 will be our only D frontier, right? Which means we have our unique D drive, which means we've solved the problem. So let me go to this table. Now this is the simplified answer. That'll be good for you to actually write down. Same thing, just really brief going through it again. We said A was 0. This implied that H was 1 and B and C were 1 because of the inputs of the initial AND gate. We have D on the output. I just added some remarks to help it make sense. So therefore, we guess D is 1, D bar, I is D bar, we propagate it through. In order to propagate it through, we say maybe we have it solved if we set all of the other inputs to that last NAND gate equal to 1, which is what we did here. We did some implications, we figured out that K was equal to D bar. Well, we already have K is equal to 1, so we have our first contradiction. So we maintain everything the same. So since E equals 1, created that error that we figured out for the contradiction, we start with just saying E equals to 1. We get rid of all of these, and that leads K to being D bar, E bar to 0, J equals 1. So that works fine. Here again, we try guessing by making L equals to 1 and M equals to 1, because those are not controlling values. So here's the implication. We figured out that M was equal to D bar, but we already defined M is equal to 1, so we have our second contradiction. Since that created the contradiction led from the fact that F is equal to 1 on the input, right? So therefore, we decided F is equal to 1, and this propagated L is equal to 1, and N is equal to, M is equal to D bar. So you have 1 D bar, 1 D bar, 1 on the inputs of the last AND gate. So that creates our unique E drive. And so we've propagated it all the way through. So if you have on a circuit for a NAND gate, right? And you have 1 D bar, 1 D bar, right? Well, it's still going to propagate D to your output. And you have multiple issues. Now, what would happen if I had D bar and D? So I had 1 D bar and D on the inputs of my NAND gate. So here I have it should be 0 and it is 1. Here it should be 1 and it is 0. What's going to be the result on the output?
0.
Correct. But it should be what?
D bar.
No. Stick with it. You were right. No, if I have all ones except 1 0 on the output of a D, right? So that's what we're expecting. What's the output of the NAND gate going to be? All ones but 1 0.
0.
On a NAND gate.
Oh, man, 1.
Now the opposite. This is where the error has occurred. So we have all ones, but then the last one is 1 0. So what's going to be the output going to be? So what's the output going to be? All ones except 1 0.
On the NAND gate?
Yeah.
1.
So both of these are just going to put a 1 on the output, right? So if you have an instance on your unique D drive where D and D bar are contradictory and everything's taken out of your J drive, but it only comes down to these contradictory results, that's where the algorithm fails. So that portion of algorithm failure, that means you can't detect the faults, that means you have to physically check for it. Now I'm not going to be that cruel on an exam. The one thing I will guarantee is that the algorithm will work and you will be able to propagate to the output. You just have to the last portion of the problem is you have to present the specific test vector. So we had A equals 0. We were able to figure out B is 1 and C is 1. D is equal to 1. E is equal to 1. And F is equal to 1. So that's your input. So that's the conclusion of the correct answer. And putting in a table like this is sufficient, especially with remarks, because remarks will help me determine any error carried forward or logic errors. So I can give me a reason to give you points. All right, so does anybody have any questions on the D algorithm? Or any other error propagation? I don't know if any of you will still be around, but I will, in 2 years, be offering a undergrad/graduate course in testing and fault tolerance. So this is, you know, this goes a much deeper at this level though. For CMOS, this is sufficient to understand that, you know, that once you synthesize the circuit, you need to figure out some sort of testing. There's troubleshooting if you're trying to figure out a small circuit. If you get a slightly larger circuit, that can become problematic. Before you use this automatic test pattern generation, you can use your propagation justify algorithm, or you can use your D algorithm if you know there's fan out. Yes?
For AND gates, whenever we input 1 in D bar, we get D bar, right?
Yeah, for AND gates, you get, yeah, so basically here, for D bar, it should be 0. I mean, it should be 0, but is 1. Yeah. And therefore, on the output, it should be 0, but is 1.
And for NAND gates, if we input 1 in D bar, we still get D bar?
No, for 1, so it should be 0, but is 1, right? So it's NAND gate. So 1 and 0 should be a 1, right? Because it's NAND, but we're actually going to get a 0 on the output for a NAND gate. So this becomes 1 in D bar becomes D.
So up there, if we look at the thing, whenever we set
Which thing?
D, whenever we put lowercase d to 1, and then we inputted D bar as well.
Oh, it should be 0, 1, 1, right? So it should be D bar. So this should be D.
This should be D, yeah.
D is at I. And put it as G. However, oh, that fails because of the contradiction. So then, oh, so this should be 1, 1, 1.
Oh, is that D?
Yeah.
G's D.
Mm-hmm.
Yeah. Okay.
G is D, and that's going to give everything's going to be D bar. I see what you're saying. Yeah, this is D, not D bar.
Yeah. Okay.
Yeah, that's what it is. So G is D. Propagate G to D. Any other questions? That's the right kind of question, though.
I read propagate D to G, but I wasn't.
No, it's fine. It's
sure.
That's why I always stop and ask, because I want to make sure that everybody's kind of read it properly. And in the table here as well, G is equal to D. Okay, so I want to, from here on, about testing, there's going to be testing and kind of some understandings of some logical fallacies. It's 2:10. You know what? We're going to stop here. So we're going to go all the way up through the D algorithm. Here's what's going to work for the rest of. We're going to finish up section 6 next lecture. Next lecture is going to be where the material for the second take-home exam is going to end. So you're going to do this assignment over the weekend. I'm going to email you my edits back to your essays. Here's the way this next week's going to work. Tuesday, TGOs are going to be due as normal, right? Thursday, you're going to get your final edits to me for the essay, and more than likely I'm going to approve them, and then you're going to post them to send a week. And then Thursday, you don't have to worry about submitting the TGOs because I want you to have them with you when you're doing your take-home exam. For the rest of the semester, I'm going to be teaching design concepts using the tools. So this will be the end of the exam type of material. Everything else, you're going to have 4 labs. And so what's going to happen is the material that I cover in class, those kind of TGOs, you're going to put them in the lab report. and then from there you're going to use. I'm going to have those designed in such a way that if you follow it, you'll be able to complete the assignments. The labs are designed to emphasize good design fundamentals. They're not supposed to be very time intensive. You almost think of them like, if you recall from your initial coding classes and they say, all right, well, here's a small function, follow these steps, and you'll get this. But the whole goal is you're going to be learning, okay, I'm going to put together a NAND gate in this tool. I'm going to actually use Spice to be able to simulate IV curves like we learned previously. Oh, I can actually use some Verilog to actually build up a circuit. And the end goal is you're going to be putting a Verilog MIPS processor, making some minor Verilog. You're actually going to have it fabricate, you're going to put it in a pad frame, and then you go do tape out. So you're actually going to be taking a technology file and being able to figure out its power consumption, its performance, and its accuracy. And so all of those, this is where all of those skills that I checked off and I showed you those job descriptions, that's where you're going to be able to do that. So now that you've done Addy Algorithm, you've checked off another one, Atpg. So, does anybody have any other questions before I conclude lecture? All right, have a good day. Yeah, I'll post it.
Okay.